Well, good afternoon, everyone. My name is Carol Barrera, and I'm a geoscientist at the U.S. Geological Survey Earthquake Science Center in Menlo Park, California. And today I want to show you the regional geophysics of Indonesia. Well, so here is the outline of today's lecture, whose objective is to present some of the most interesting features that can be identified in the geophysical data. And so let's start. Here is the location of the study area. We are at Southeastern Asia. And as you can see, we can divide these into two regions. The interaction of the Sonda plate, which is the southern segment of the Eurasian plate, with the Indo-Australian plate at the southwest in a relatively simple tectonic setting, and a much more complex interaction of this plate with the Australian and the Philippine Sea plate, together with some oceanic crusts that were embedded during the tectonic evolution of the region. So before I continue with the geophysical anomaly maps, I want to briefly explain the gravity and the magnetic methods and their usefulness. So let's start with the gravity anomaly, which allows us to study the density properties of the subsurface of the Earth. So to achieve this aim, we first have to measure the gravity field of the Earth. And one method to do this is with satellites. So here are two examples. And they are very interesting because both of them uses different methods in order to measure this gravity field. So the gravity recovery and climate experiment measures this gravity field by calculating the influence of this to the variation of the distance of both of these satellites. And the Gauche is equipped by gravity gradiometer, who measures the differences on the gravity acceleration. And this video shows that compiling both of these data sets results in an enhanced gravity field model. So after making these measurements, we want to isolate the geological contribution of this gravity anomaly. And in order to do that, we have to perform some corrections. So I'm going to explain the corrections that must be applied to get the simple Bouguer anomaly, which is the one I'm going to use later in the maps. So as you can see at the right side of the slide, here is a model of a cross-section of the Earth. And on top of it is the gravity anomaly that will be measured over it. And we are going to see how, after applying these corrections, this anomaly shape changes. So the first correction that must be applied is the removing the theoretical gravity, which is the gravity that will be measured over the reference ellipsoid. This reference ellipsoid is the theoretical shape of the Earth. So as you can see here, the shape of the anomaly didn't change a lot, but the magnitude of it did. Later, we have to take into account the elevation effect on the gravity measurement. So as you can see, as we go higher in topography, the gravity anomaly decreases a lot. So we have to perform this correction. But later, we also have to take into account the mass effect in the gravity measurement. As you can see, because as you can see here, with only this correction of the elevation effect, we have a strong correlation of the gravity anomaly with the topography. So in this way, we finally get the simple Bouguer anomaly. So this this anomaly was downloaded from the calculation service of the International Center for Global Earth Models, which is provided by the German Research Centers for Geosciences, as well as the International Association of Geodesy. And the parameters that were selected to perform this anomaly was the agent 64 for the gravity model, which compiles both the satellite data of the Grace and the Gauche satellites, as I showed before, together with the Earth gravity model of 2008, which compiles ground data and airborne data. And these are the parameters that the calculation service uses in order to perform the corrections I explained before. Now let's move to the magnetic anomaly, which is the anomaly generated by the interaction of the Earth's main magnetic field with the rocks at the subsurface or surface of the Earth. And I want to explain an interesting feature that is related with the magnetic polarity reversal, and that will help us with the interpretation of the magnetic anomaly maps later. So this magnetic polarity reversal occurs in different intervals of the time, and the rocks generated at the oceanic spreading ridges can record these polarity reversals, creating magnetic strips. Cool. To develop the magnetic anomaly map, I used the third version of the Earth magnetic anomaly grid, which is 2 arc-minute resolution, and it is compiled from satellite, ship, and airborne magnetic measurements. An interesting characteristic of this magnetic grid is that it doesn't include prior information as other models does. So this is very good because it gave us the confidence that the anomalies that we are seeing are not strongly correlated with mathematical or predicted observations. Also, let's start with the maps and the interesting features that we can interpret about them. So the first map is the Fourier anomaly. And as you might remember, this anomaly is obtained after applying the elevation effect correction, but before applying the mass effect. So it is strongly correlated with topography. However, we can interpret very interesting features about this map. As you can see here, these bulges are the flexures of the tectonic plate as it collides with the sonda plate. And we also can see very clearly the morphology of the subduction zones as I highlight here. So here is a map of a previous lecture where you can see that the location of the trench, of the important trench, so like the Sonda Java, the Philippine Trench, the Sulawesi Trench, the Timor Trough, and the Seram Trench are very well represented in this map as well. So it is very clear the 4 arc in front of this trench, as well as the volcanic arc that is generated because of the subducting slab. As we can see here, the volcanoes correlates very well with the high positive gravity anomaly. So let's move on with the Bouguer gravity anomaly, simple Bouguer gravity anomaly. And as you might remember, this anomaly was obtained after considering the excess of the mass related with the topography. However, this correction doesn't contemplate the low density route that supports the topography. So for that reason, we obtain strong negative anomalies beneath the continental crust and strong positive anomalies beneath the oceanic crust. However, there are some exceptions, and I want to call the attention into the Molucca Sea, because as you can see, the Molucca Sea plate is an oceanic crust, so we might expect a positive gravity anomaly. However, the collision between both of these arcs, the Sanji arc and the Almahera arc, because of the double subduction of the Molucca Sea plate beneath both of them, has created the thickening of the sediment layer above it, thus creating a negative anomaly, simple Bouguer anomaly. This double subduction is supported by seismic data, as you might have seen in previous lectures. Well, so in order to get more information about the gravity data and also to facilitate the geological interpretations, I performed a transformation following the book of the doctor in geophysics, Richard Blakely, which is called the upward continuation. So the upward continuation consists on transforming the data as if it was measured in a much higher elevation. In this case, I used 40 kilometers. So this enhanced the long wavelength of the gravity anomaly that is caused by deeper structures, giving us the regional anomaly. So this is used in order to calculate the residual anomaly. And the method to do this is taking the simple Bouguer anomaly, as you can see again, this sketch, and subtracting to it the regional anomaly that was obtained by doing the upward continuation in order to get the residual anomaly, which is the gravity anomaly due to shallower structures. So this is the result, and as you can see, this is a very complex map because of all the features that can be interpreted and studied in it. But I want to highlight the most important one. So first, again, as with the Bouguer anomaly, we can differentiate between the continent and the oceanic crusts. But in this case, with the residual anomaly, we also can see the differences in the thickness of the crustal and sediment layers. So as you can see, the darker blue corresponds to the thicker sediment and crustal layers than the lighter ones. We also can see the features that are related with the tectonic evolution of the region, as here the deformation of the Sonda plate in this place because of the highly oblique collision with the Indo-Australian plate. Also, the ocean plates that have been consumed as this one between Sulawesi and Borneo, and also beneath the Celebes and Sulu Sea, as well as the deformation of other oceanic crusts like the one beneath the Banda Sea. And also we can see the new oceanic crusts that have been generating in the northern region of the study area. Also, something really interesting is that it allows us to see structures that we couldn't see in other maps, as this positive gravity anomaly at southern Java. So this positive gravity anomaly was studied by Cobb and other scientists in 2002 by using wide-angle seismic data and gravity modeling. And they proposed that this positive gravity anomaly is caused by two reasons. That beneath this, there is an oceanic type crust, and also the mantle is very shallow. So both of them, as they are as they have higher density, they generate this positive gravity anomaly. So here is the magnetic anomaly field, and as I explained to you before, these magnetic strips allows us to know in which direction the oceanic crust was generated, as the stripes are generated at both sides of the oceanic spreading ridge. And it's also interesting to see the difference of the magnetic anomaly in the subduction beneath Java compared with the subduction beneath the Sonda Trench. And this can be generated mainly because the collision of the Indo-Australian plate beneath Sonda in the Java region, it's mainly almost in an orthogonal way, while beneath the Sonda Trench at southwest Sumatra, it is in a highly oblique way. Cool. So the conclusions about this study are, first, that the geophysical data analysis is a powerful tool to reveal the physical properties, in this case, density and magnetic properties, of the crust and the mantle. Then, that the gravity anomalies are closely related with the active tectonics of the region, as we could see the morphology of the subduction zones, the formation of new thin oceanic crusts, and the deformation of the Sonda plate because of the tectonic evolution of the area. And finally, that the magnetic anomalies are strongly related with the properties of shallow crust, and the magnetic strips are parallel to spring axis of newly formed oceanic crust. Well, so thank you very much for your attention.